so what we're going to talk about now are assays for DNA replication. So how do you tell if I give you a clear solution, okay, and biologists work all the time with clear solutions because most enzymes aren't colored, okay? There are a few of them that are, things that bind iron or GFP or other fluorescent proteins, but for the most part, if you get a pure solution of an enzyme, it's going to be clear. And more importantly, it's not going to tell you anything a priori about what's in it unless there's a label on it, okay? And most of the time, when you're trying to understand a complex reaction, there are no labels associated with it, okay? You just have tubes that have some will and some won't have your activity in it. So how do you assay for DNA synthesis? And we're going to go through assay for really DNA polymerase activity. So we're going to go through several different approaches, and we're going to talk about how they are, what they're good for and what they're not good for. Okay? So the first type of assay we're going to talk about is a simple incorporation assay. Okay, and this is a type of assay that can basically be used with any polymer, right? Not only in biology, but also in any other setting in which you're making a polymer. You can use this type of assay to assay the formation or synthesis of that polymer. Okay, so this works by, you need to be able to separate the polymer, in this case DNA, from its building blocks. In this case, DNTPs. Okay? And this, although we're going to talk about this first in the context of DNA replication, this same type of assay could be used for transcription, for protein synthesis, and any number of other types of polymer synthesis events that you can think of. For example, you could use it for glycogen synthesis, which is also a polymer synthesis reaction. Okay, so how do you go about doing this? How do you typically do this sort of assay for DNA replication? So what we need is a primer template junction, because you need that for any DNA synthesis reaction. Okay, so the first thing you do is create a primer template junction substrate. Okay, and what I'll tell you is typically for DNA synthesis reactions, what people will use is you can take a phage called M13. It has a large single-stranded DNA genome, okay? And you can make these single-stranded DNA circles. Okay? We know the sequence of that genome, and so you can synthesize, and this is, in the case of M13, 5,000 base circle. Okay? And then you can synthesize a not to scale, okay, typically 20 to 25 base pair primer. Okay, so that gives you a primer template junction, and just so you know, from now on, when I have an arrow, the end of the arrow, consistent with that being extended by DNA polymerase, will always be a 3' OH. The arrowhead end of the arrow will be that, and the other end will be the 5' phosphate. Okay? Where do you get these primers? Well, these days you put it in a computer, send it to a company, and they synthesize it for you, and they send it to you the next morning. Okay? It's very wonderful. Okay? Whatever sequence you want, you can have the next morning as long as it's under 50 base pairs or so. Okay, so we have our primer template junction. We make this, by the way, by taking that primer and the single-stranded DNA, heating it to 100 degrees in a heating block for like 3 minutes, taking the heating block out of the heating element and leaving it there while we go to lunch. Okay? When we come back, it's annealed. Okay? That's the really easy way to do that. Okay, so we have a primer template junction. Now we add to that the buffer that we need for the reaction. Okay? For most polymerases, this is going to be a neutral pH buffer with usually between 50 and 100 millimolar salt, and with magnesium acetate or chloride or some other magnesium providing solution. That needs to be usually around 1 to 2 millimolar. Okay? So we have a buffer that has the right conditions plus the DNA polymerase, or at least the solution that we think has DNA polymerase in it. Okay? We start the reaction by adding DNTPs. Okay? And what's critical for this assay is at least one DNTP must be labeled. Okay? And typically this is either a fluorescent label or a radioactive label. Okay? The fluorescent labels are almost always on actually a thymidine analog, so it's added to the base. It turns out where the methyl group is on a thymidine, you can put pretty much anything you want there. Okay? It can be huge. It can be like a 7-ring structure hanging off the end where that methyl group is, and the polymerase is like, cool, I'll add that, no problem. Okay? If it's a radioactive label, either you use tritium substitutions within the bases, or you use a P32, a phosphorus atom, in one of the phosphates. Which phosphate do we modify? Alpha, beta, gamma. Alpha, right? We do beta or gamma. It's not part of the product, right? Okay? So those are the two ways that are typically used to label. Okay? And at that point, the reaction's going, because you've got all the components now, and it continues. You basically take time points. And for each time point, you separate. Typically, what you would actually do is add SDS or something to kill the reaction, or you could add EDTA. Okay? You can stop a reaction. Okay? But then at the end, I shouldn't say end. How about each time point? You would separate the DNA from the labeled DNTPs. Okay? So basically, if you have productive synthesis, some of those labeled DNTPs will now be incorporated into DNA polymers, and the rest of them will be still in this. So we have to have a very efficient way of getting rid of all the labeled DNTPs from all the DNA, and then we can just measure how much labeled DNTPs are part of the DNA at this point. So if you imagine that we are looking at this substrate up here, right? Most of the DNA, well, all of the DNA is unlabeled to begin with, but then when we synthesize new DNA, the new DNA will be labeled. Okay? So we just need to figure out how do we separate that pink DNA from the little pink nucleotides that are floating all around it. Okay? And it turns out there are many ways to do this, or at least several.